why are we here and what's happening? So this is not just Manitoba, it's globally. We're seeing how our paradigm to energy and our relationship to energy is really shifting. We know energy is everywhere, and as the shift happens, our relationship to energy is also shifting. And this is why not only will the cities be different tomorrow, but our buildings will also be different. They're not going to be the way they are today. It'll be really, how do we get there? We got to think out of the box in order to make that happen. And so as this energy landscape is changing in the era of energy transition, more renewables are coming online and more technology is beginning to integrate AI or artificial intelligence. But we know many people are still frustrated with the prices of energy, particularly our electricity. Costs seem to be increasing, while we have so many other challenges on our plate as well. I just always like to bring attention to the fact that our baseline in Manitoba is far more affordable than it is in remote Manitoba. The prices tend to be 37 times higher or more than our urban baseline, and it just depends on the type of accounts that happen up there. So perspective-wise, getting control over our energy costs, our energy usage, as well as how we supply our energy is really important to being able to afford our energy and our lifestyles. So while this is happening, we also see this massive drop in renewable technology. We have the price of solar and wind dropping, and this results in this unprecedented adoption of renewables, but yet we see this ever increasing demand of energy on the other side of that balance. And we are also seeing the rise of the prosumer. The prosumer is a consumer who no longer only consumes power, but also sells it back to the grid, sometimes just in excess, in the case of, say, like a home, or sometimes as a pure business due to the progressive energy policies that enable this to occur, as well as the rise of corporate PPAs, which are power purchase agreements. And we still are in times of frequent natural disasters happening, just changes in climate that are unprecedented. And this leads to strange phenomena all over, from hurricanes in the Caribbean to ice storms in Texas, as well as we know in remote communities, the impact of cold climates and what that means for lifestyle. So smart electrical demand management comes in this era, excuse me, with these dynamic technological advancements. And as this ever-growing dependence on electricity happens, we see the importance of having efficient electrical demand management. It's just paramount. And SEDM emerges as this transformative solution. It offers these nuanced approaches to addressing this escalating demand on our power grids. And our resilience on electricity continues to escalate. These traditional ways of demand management become increasingly evident. We see a change there. So from peak load challenges to limitations of static infrastructure, there's this urgent need for innovation and the way that we handle and distribute electrical energy. So SEDM is the answer to this pressing need and presenting a paradigm shift in how we approach energy consumption. When we can integrate cutting edge technologies and real-time analytics and intelligent infrastructure, SEDM comes in and aims to optimize this utilization of electrical resources in a way that is both sustainable and economically efficient. So just to bring your attention to some of the traditional demand management challenges, I just thought I'd put it out there to show some of the challenges that we face. Having limited visibility and control in the existing system often lacks this real-time visibility into energy consumption patterns. And this limitation hampers the ability to make these dynamic adjustments to energy usage and respond promptly to demand. We have traditionally static load forecasting, and this relies on these static models that might not accurately predict variations in energy demand. They can lead to overestimation or underestimation of required resources, and that can affect grid stability and efficiency and, of course, cost. We have peak load management issues. When we're managing peak loads, it's a very complex task in these traditional systems. These sudden peaks in demand, especially during peak hours, can strain the grid and lead to higher operational costs, environmental impact, and potential grid failure risk. There's inefficient resource utilization, which can often lead to struggles to optimize the use of available resources. This inefficiency results in this overuse of non-renewable energy resources and an underuse of renewable energy when it is abundant, as well as issues with limited consumer engagement. So traditional models have limitations on how consumers actively participate in this energy exchange. And without real-time feedback and incentives, consumers might not be motivated to adjust their energy use patterns to align with what the green grid may need or energy conservation goals, as well as a lack of flexibility. So traditional systems have this lack of adaptation to dynamic changes in this energy landscape, and that again doesn't really align with this integration of renewable energy sources that are quite dynamic. And then there's this growth of electric vehicles that's coming online, as well as consumers becoming more involved and evolving in their behavior with their relationship to energy. And there's also this difficulty with demand response, which is implementing effective demand response programs. They challenge, there's a challenge in the traditional demand management of it. So coordinating responses from consumers, industries, other stakeholders in a timely manner, it just requires more advanced and responsive systems to do that effectively. We also see the risk of grid overloads, where traditional systems face difficulties in anticipating and managing grid overloads. Sudden surges in demand or unexpected events can strain infrastructure and lead to reliability issues and potential service disruptions, as well as limitations with emerging technologies. So as we are emerging, we have advanced analytics, machine learning, smart grid infrastructure, which are crucial for enhancing efficiency and responsiveness, but there's this lack of integration for that. And then, of course, environmental impact with traditional systems that are focused on reducing the environmental impact of energy consumption. And there's like a lack of emphasis on sustainability that can contribute to these increased carbon emissions and other negative consequences. So we've got a lot on our plate in the traditional sense, but we want to move towards efficient electrical demand management. This really is where we're going to see savings in terms of costs, where we can manage our peak demand costs and electricity costs that vary throughout the day. When we can take control of this efficient demand management, we can find those strategic shifts in what to do and when. The grid reliability, again, balancing the supply and demand equation will help us to reduce risk of blackouts, system failures, any spikes, and just lead to greater reliability. If we can, if we can avoid, I think I scrolled a little too far here. There we go, apologies. If we can avoid overuse of wasteful consumption, then we're going to have resource optimization, as well as if we can have a better way of facilitating renewable integration, we'll become more efficient with our demand management facilities and improve that connection, that balance, as well as leading to better infrastructure planning. Once we know what kind of feedback we're getting on the demand side, we can make better policy plans and help utilities as well as policymakers anticipate future needs. And again, promote sustainable practices with energy conservation, and then finding those sweet nuggets of reduced operational costs so that our facilities and our institutions and our buildings as well as a whole can have better financial stability in business by reducing operational costs. And of course, meeting energy efficiency standards and targets that are being set in the regulatory environment, avoiding penalties and contributing more to sustainable energy landscape will lead to regulatory compliance. So I thought I'd go into some of the components of what happens in terms of devices of core components of SEDM. And we'll talk a little bit here about the IoT devices, which are the Internet of Things devices and sensors for real-time monitoring, as well as the importance of data analytics and machine learning for predictive modeling as we move forward in this area, and then what some of the smart grid infrastructure looks like for dynamic control. So when we look at the different IoT devices out there, there's a whole scope, and this is just quite a comprehensive overview of some of these devices, but it's not the, of course, complete list. with the most critical ones being smart meters. These are meters that are key components in residential and industrial settings. Sometimes they're referred to as bidirectional meters. They provide real-time data on energy consumption, and they allow users and utilities to monitor usage patterns and identify any inefficiencies and optimize energy consumption. We see a lot of smart thermostats in homes these days. These are the residential and commercial building thermostats. They collect real-time data on temperature, occupancy, usage patterns, and this information is used to optimize the HVAC systems for heating, ventilation, air conditioning, and reduce energy consumption costs. Current sensors are used to measure the flow of electric current in a circuit. These sensors provide real-time information on energy consumption at specific points in the electrical grid, and they aid in load balancing and optimization. There's also voltage sensors that monitor the electrical potential difference in a circuit. They provide real-time voltage data. These sensors help stabilize the grid and identify voltage fluctuations that may impact energy efficiency. Now, many people might be familiar with smart plugs. If you have these in your home, they can be added to the traditional electrical outlets, and they monitor energy usage of connected devices and appliances, and they provide insights into individual consumption patterns and allow users to take control and schedule their operation. There are environmental sensors, such as temperature and humidity sensors, and they're used to collect data on surrounding conditions. In SEDM, these sensors can contribute to optimizing energy usage by integrating environmental factors into demand forecasting models. Now, also occupancy sensors are important. They detect the presence or absence of people in a space. In buildings, they could adjust lighting. There could be HVAC system control aspects to it and other energy consuming devices based on occupancy, et cetera, that help to contribute to energy savings. Smart lighting systems incorporate sensors to detect ambient light levels, occupancy, user preferences, and so on. This data is used to adjust real-time lighting and, of course, optimize your energy consumption while maintaining adequate illumination. And flow sensors are important in industrial settings. These sensors monitor the movement of liquids and gases in a process requiring energy, such as manufacturing or water treatment facilities. These sensors provide the data for optimizing the energy-intensive operations. And what we're seeing a lot of now are the integration of the supply side, which I'll get into shortly, on solar monitoring systems. These use sensors to collect real-time data on solar panel performance and sunlight conditions and how that integrates into the building and the energy production. So this information helps to optimize the integration of solar energy into the grid and manage energy demand. So these devices really enable that granularity and that understanding of energy usage patterns that facilitates the real-time decision-making, and it contributes to the overall efficiency and sustainability of the electrical grid. So coming back to this equation that I was talking about, today we're really focusing on the demand side, but this energy balance also has the supply side. So DSM stands for demand side management, and SSM is supply side management. And these two strategies are aimed at optimizing the generation and consumption of electricity. SSM focuses on managing the generation side and the supply of electricity. So it can involve enhanced energy efficiency, reliability, sustainability of power generation and distribution systems. Whereas the demand side focuses on managing and influencing the patterns and levels of electricity consumption by end users. And that side of the equation has the goal to optimize the use of electricity, reduce peak demand, and enhance overall energy efficiency. And so the relationship between them helps to contribute to the overall efficiency and sustainability of the energy system. Again, just to remember, supply side, you're thinking generators, distributed energy resources, that's that side. When it comes to everything that's happening within the building or the demand and the usage, that's the D side that focuses on influencing consumer behavior as well as what's happening to encourage efficient energy use. Now, I wanted to touch base on predictive modeling in SEDM because with this, just where things are with AI and machine learning, there's a lot of talk of this. And I wanted to show how it is really across so many dimensions in our energy system. Our load forecasting models will have data analytics and machine models built into them where they can predict future energy demand based on the load forecasting, that the data that's collected. And it helps to utilities to anticipate peak periods and optimize resource allocation, enhance grid reliability. We use predictive modeling and energy consumption pattern analysis, which shows the way that the patterns of the energy consumption, and it again helps to predict demand. Predictive maintenance for grid infrastructure has machine learning built into it to predict potential equipment failures, identifying issues before they occur. Think of your maintenance needs, think of preventing downtime, anything to just the overall reliability of the grid requires that. In demand response optimization, this is where we see predictive modeling deal with the high energy demand, and it facilitates the response program. So it's where we see incentivizing customers and automated systems to adjust energy usage during peak times. In renewable energy integration forecasting, this is where we see the availability of renewable energy resources coming online on that supply side balance. And this information helps the better coordination of the energy distribution and efficient integration of both sides of that equation. Anomaly detection is important. This is where we see unusual patterns in energy consumption, predict events, perhaps could be equipment malfunctions, cyber threats, sudden changes in demand, things like this. Customer behavior analysis is also quite an important factor in electrical demand management because it's hard. Everybody's different, right? And so predicting customer behavior preferences based on historical energy use can help us to predict future consumption patterns. And so utilities tailor programs and incentives and communication strategies around encouraging efficient practices. We have dynamic pricing optimization, where models predict periods of high and low energy demand. They enable utilities to implement dynamic pricing, and they adjust pricing based on that real-time demand forecasts in different jurisdictions. And they encourage customers to shift their energy usage to off-peak hours. Imagine paying less for doing your laundry at midnight kind of thing. Fault detection is important in distributed energy resources, and this comes from analyzing data from the DERs, that's the distributed energy resources, like solar panels or energy storage systems that detect faults and deviations from expected performance. And that comes back to detection and timely maintenance and optimization, so we don't have blackouts, brownouts, or other trips in the grid stability and reliability. And energy consumption forecasting for EV charging. EVs are coming online. There's it's just the pace that it's happening at is quite rapid, and we're seeing a lot of it come online, not only just people driving them in your community, but the impact on the grid. And so machine learning models help to analyze the data of the EVs, their charging patterns, different traffic conditions, charging station availability to help predict that future energy demand for EV infrastructure. Again, that comes back to planning and optimizing charging locations, capacity policies, and so on. So you can just see how throughout the system, artificial intelligence, machine learning, predictive modeling, all of these aspects are really impacting where we're going in the future, and our ability to integrate data and transform that into smart decision making, which leads to smart grid infrastructure, which again is that key enabler of this dynamic control in this SEDM. And this involves that integration of advanced communication and sensing. So here you're going to see a lot of different acronyms. I'm going to go through them because they're quite long. So you can have that in your background knowledge in your toolkit. So AMI is advanced metering infrastructure. This has to deal with smart meters and two-way communication capabilities that are essential to AMI. And again, think real-time data exchange between utilities and consumers. That's what's happening there. The bidirectional meters would fall under AMI, advanced metering infrastructure. And these things, again, support dynamic pricing, demand response programs, accurate monitoring of energy consumption. When we talk about DMS, that's distribution management system. And this comes down to real-time data from sensors across the distribution grid. This is what enables utilities to monitor and control the distribution network dynamically, which helps to do optimization of voltage levels and respond swiftly to faults or outages. When we think of WAMs, we're thinking wide area monitoring systems. This has to do with synchronized measurements from geographically dispersed sensors to monitor the overall health and stability of the grid. It provides real-time situational awareness, enabling operators to make informed decisions for dynamic control during contingencies. You may have seen PMUs, which are phasor measurement units. They measure the magnitude and phase angle of electrical quantities at high speeds, and they're deployed across the grid so utilities can obtain synchronized phasor measurements, and they facilitate that real-time analysis and dynamic control for grid stability. DRMS is Demand Response Management System, and it communicates with smart devices, such as smart thermostats or appliances to dynamically control energy usage and the response to grid changes. And of course, pricing involved in that. Grid automation and control systems leverage real-time data to optimize the performance of grid assets. This is things such as reclosers, capacitor banks, voltage regulators that are dynamically controlled to enhance grid efficiency and reliability. Then comes the energy storage part. Energy storage, or ESS, are things like batteries that are integrated into the grid to store excess energy during periods. Now, it's not only batteries, but those are the most commonly known at this. I'll leave it in the scope of this discussion. That could be a whole other conversation. But what they do is allow a dynamic control of energy storage that helps to balance supply and demand and actually contribute to grid stability. Of course, if you're in remote locations, this is your backup, right? And sometimes even in the city, I should say, some of the homes that we've done with our smart microgrids are grid connected, but they can island as if they were not connected because of their battery ESS systems. EV charging is an important part of smart grid infrastructure, which integrates into the grid. It allows for this dynamic control of EV charging, and it helps utilities to optimize charging patterns and consider grid conditions, renewable energy availability to support that and other demand fluctuations. Smart grid sensors, you've probably seen some of these. I mentioned some of them earlier. They include the voltage, the current, the thermostats for temperature. They're deployed throughout the grid. These sensors provide the real-time data and monitoring of those conditions, again, dynamic control assets. And of course, don't forget our communications networks. So important because these robust communication networks, the fiber optics or wireless technologies, they connect the smart grid components, and they enable rapid data exchange and control signals between devices. And I hope that helps to understand why this is so dynamic in the decision-making processes in these grid conditions of where we're going in smart energy demand management. That really gives you a sense of that infrastructure part to it. And this is what it comes down to is really this energy resilience. And when we put these transitions into effect, into our homes, into our buildings, this is what we start to see. We see action and we see benefits of the results. This is an example of just one of our clients that I just remember getting this feedback from them, and it really shook me to my core to how important the work is that we're doing. We might not always see it, but this energy transition is really enabling life-saving measures, even in our city. This family happened to have their lights on and internet in the neighborhood when nobody else did. And it was really important for them, for their family and the special needs of their family. So where are we going? Canada has a target of 100% net zero emitting electricity by 2035. We have a ways to still get there. That's only part of it. The big part of it is the demand side. When we look at the supply and the demand, when we flip that coin, we could put 45% to the supply side. Let's just say we're going to electrify everything and supply it that way. But the other half really is what are we doing when we electrify our vehicles? That's 30% in processes if we electrify everywhere. And the other 25% would go to reducing energy for efficiency and circularity, meaning through the design and build of low carbon infrastructure, measuring, monitoring, saving, and of course, circularity for sustainability. I just wanted to mention a little bit about microgrids because you've probably heard me speak to them. A microgrid is a group of interconnected loads and distributed energy resources that act as a single controllable entity with respect to the grid. They can be disconnected from the grid to operate in grid connected mode or island mode. And microgrids can improve customer reliability and resilience to grid disturbances. What's really important to see here is, yes, there's the generation and storage and the network part, but the demand side, it wouldn't be able to function the way that it does without the demand information and smart demand information. When we look at this from a higher zoom out of what that could look like in a community or an area, the demand side is so critical for a microgrid to function. And so as we are so focused on the hot topic of microgrids, which is fantastic on the supply side, we can't underestimate the importance of the demand side and getting that infrastructure up to speed on the communication and the ability for it to respond and integrate to supply side that is transitioning so quickly in terms of its responsiveness and artificial intelligence and so on and so forth. Okay, let me see if I can flip this. Okay, so some of the benefits you may be wondering of SEDM. I've mentioned the energy cost savings for consumers and businesses, the reduction in the carbon footprint and the environmental impact, and the improved grid reliability and resilience. Those are key parts to it. I wanted to show you some examples of what that might look like in terms of cost savings. You might be thinking energy efficient appliances and equipment. These are great. You can invest in energy efficient appliances and equipment. And this is the typical things that we're seeing. Some of these appliances are becoming smarter and more integrated so that they can respond to SEDM, going beyond just Energy Star ratings. So keep that in mind. LED lighting, moving to bulbs is a cost-effective measure. They have longer lifespan and so on. Home and building energy audits are becoming a bit more normalized now. We're seeing this, unfortunately, the federal Greener Homes Grant is fading out or sunsetting, but that had a lot of home and energy building audits be processed, where consumers and businesses conduct these audits to identify areas of inefficiency and then think of transition methods. Mentioned the smart thermostats. Time of use pricing is an incentive for consumers and businesses to shift energy usage off peak hours. The demand response programs are very important too to reducing energy consumption during peak demand periods. We talked about renewable energy adoption. Energy efficient building design. This is where buildings, as in our organization today, can invest in energy efficient principles. They incorporate features, proper insulation, and so on, but also going beyond that to now include those smart devices so that the buildings can breathe, in a sense, not only just with the physicality of it, but in the devices that are in there and provide information on that pathway of both feedback and feeding it so that we know what's happening in the building. And that's what I mean by living that building coming alive. Energy management systems allow businesses to monitor, again, control, optimize your energy usage. Employee engagement programs are really important too, as we see moving forward in this transition to influence in a way that, a positive way for people to have an ownership and a responsibility to the energy that they use to identify wasteful practices and so on, as well as upgrading any HVAC systems is always important. So carbon footprint and environmental impact is important to be reduced. It's an integral goal of smart electrical demand management. I wanted to put this into a pie for you to show how it's not just one or the other. It really is important to come together so that, there's an aspect of renewable integration, but also the energy efficient demand response for that dynamic control of what's happening on the other side of that equation. Putting in the smart appliances, of course, dealing with green building energy optimization, putting those practices into place, having carbon aware grid infrastructure, which relies on smart grid infrastructure to be designed to be carbon aware. This integration of renewable energy and real-time monitoring and dynamics ensures that the electrical grid operates in this environmentally conscious manner. There's also the smart transportation aspect. How are we charging? When are we charging? The dynamic information going back and forth with EVs, and then carbon offsetting programs and so on. And so there's many, many parts to it, but that just gives you a sense of how we can impact that. And then, of course, grid reliability and resilience initiatives. There's many. I thought I'd just throw them down for you to consider. There's so many aspects to it. We could focus on just one for a conversation, but everything from dynamic load balancing to real-time fault detection responses, Automated grid restoration is really important to help us get back up with grid reliability and the resilience of it. Adaptive protection systems are those that dynamically adjust based on grid conditions, and they build that resilience into the grid by providing tailored protection against different types of disturbances. Integrated microgrid systems, that just really helps to build resilience on the supply side, as well as the device capabilities on the supply side, enhancing the integration and interoperability of the supply side. So how it's communicating and almost like forcing it to step up its game on the supply side. So you, on the demand side, so you know what's happening on the supply side. So yeah, that's a really great benefit of and what we've seen with integrated microgrid systems. Grid monitoring and predictive analytics are really important, again, coming down to building resiliency. Resilient communication networks, how are we building more robust communication infrastructure is going to be really important coming down the line. As well, I talked a little bit about the demand response as a grid support is also important during peak demand and emergencies. SEDM can dynamically engage in demand response initiatives, and it reduces the stress on the grid and enhances overall responsibility. DERs, if you aren't familiar with it yet, you will be by the time I finish speaking, because I feel like I'm saying it all the time. Distributed energy resource is so important. And again, that's the generation and the storage aspects. So solar panels, batteries, etc. Just to be strategically placed across the grid to provide that diversified and distributed energy approach, which would enhance grid resilience and reduce dependence on sort of centralized resources that we've been used to. Cybersecurity is really important, sometimes gets overlooked, but it's a critical aspect of SEDM as we move to more online and transition communication methods. So robust cybersecurity ensures this integrity and resilience, and it protects the grid from cyber attacks and unauthorized access. Training and simulation, always important. We need skills. We know there's a lack of skills in our sector. We really need to improve how we are going to train people to get up to speed on where we are moving so quickly. So having programs in place and operators as well, simulation opportunities to see how these technologies integrate and behave and get trained on that is quite important. And again, flexible grid planning, coming down to that adaptability and ensuring that the grid can evolve in response to emerging technologies is absolutely important in considering environmental needs and different evolving demand patterns and that long-term reliability. So let's look at some case studies. We're just going to jump into a few of these and then some measurable positive outcomes. So in Cornwall, Ontario, Canada, this is an example of a citywide SEDM deployment. They put together a plan, and it all started by having a declaration of commitment. They said, we're going to do this. And they set a target to have this plan in place between 2019 and 2023. They had a vision. The vision was to have long-term financial planning and asset management and stewardship of their finite energy resources. They wanted to optimize delivery of services, enhance overall quality of life. And they set some goals, and that was to reduce the requirements of facilities through smart technologies, engineering standards, control, and through the purchase of high efficiency equipment and through the municipal procurement process. So with these goals, they set a target, and that target was to reduce their average consumption of 10% per year between now, which was in 2019, and 2023. So the results of that are being compiled, but you can see that by starting with the declaration of commitment at a municipal level, this is what really starts the ball rolling of making change. A smart factory. This is there's a couple examples here. I wanted to show you the cost example of, if you think about it through this cost lens, and then what does it look like through solar storage, and then plus a smart management system. So let's take a look at the blue one here first, which is the one in Minneapolis. It's a manufacturer of custom components in Minneapolis, and they set their goal to boost resilience to power outages, meet sustainability goals, reduce energy bills, and have a turnkey solution. And so the solution they brought on, they put in 400 kilowatts of solar with a battery storage system and the smart energy software. And the combined system provided the manufacturer not only with their generation needs, the utility bill optimization, but also backup power in case of outages. And the results that they saw was that the company reduced peak electricity demand, and it shifted to more favorable electricity rates and reduced their carbon footprint because of the solar that they put in. The company also purchased a system, and cash flow was net positive due to tax incentives and other savings, approximately 60% from their annual energy bill of savings. And in an outage, they had the battery storage backup for clean power for up to 2 hours for the entire facility or longer for critical loads. So that's in that situation. Now, when we look at it from a cost perspective, there's scenario one. Now we're looking on the white one with the green and the blue here, if you're following me here. The scenario here for building management system compared to a solar and battery system, you can see the savings just putting in a BMS. It still led to a net savings in annual electricity costs of over $100,000. With the solar and battery storage, they were able to save a little bit more, mostly because they probably had the generation aspect to it as well. So it does help to find net savings in when we start to know what we're doing in our spaces. Here's an example of a utility that was quite forward thinking. Fortis B.Sc implemented a software platform in Kelowna to control residential smart devices, and that helped to reduce energy use, save money, and lower greenhouse gas emissions. And then this adjusted the electric space heating, cooling, and so on. They said this. What they said was that they wanted their participants in their program to be able to meet their 30 by 30 target to reduce greenhouse gas emissions by 30% by 2030 and create more sustainable futures for British Columbians. So this was really an example of utility driven. A farm, this is a great example out of, I think it's Bundaberg, Queensland in Australia. They're a farm that does sugarcane, peanuts, asparagus, watermelon. They reduced energy 42% by implementing SEDM per ton of sugarcane harvested, which led to annual savings of over $40,000, reducing their energy and labor costs and increasing yields. The University of Calgary is currently redoing their campus. They want to create a microgrid system there. And so they're implementing not only the integration of their existing systems, monitoring, but looking at bringing on new generation as a campus model. And I just wanted to show you an example on the other side when you have the supply side of a microgrid come into a community-owned solution in Puerto Rico, for example, here. They are able to power businesses because of the power side of it, but it taps into the pharmacy, the hardware store, the bakery, the pizza shop, and so on. And they had a battery system, 700 solar panels connected to the grid. And of course, they could island or be connected to the grid in the case of an outage. So it helps to power those devices in those buildings. So lots of outcomes. We see the peak shaving and load leveling. We see demand response optimization, the real-time energy consumption monitoring, dynamic pricing strategies, energy efficient equipment management, and the predictive analytics for load forecasting, and of course the EV charging management. All right, so quickly go through some challenges and future prospects because there's a lot. I don't want to burden you with this, but I just want you to know it's out there. There's a lot of barriers. We still have a lot to do to get through this, including some of the interoperability standards that need to come along, privacy, data security concerns. Capital investments still can be quite costly, a lack of consumer awareness at running education campaigns and so on. Regulatory hurdles, limited vendor options, but we're getting better. The integration with legacy systems and some of the resistance to behavior changes. People are people, right? Again, limited incentives for utilities and infrastructure limitations. But there are trends that are coming. It's really exciting to see what's coming from blockchain energy transactions, AI, edge computing, digital twins, Internet of Things. There's 5G connectivity, machine learning, as I mentioned. I talked a lot about that for maintenance, and grid interactive efficient buildings, flexible demand side management, decentralized energy storage, and the integration of EVs. Okay, so policy and regulatory frameworks in Manitoba. You might be wondering, well, Manitoba Hydro Act is the regulation we have here, and it doesn't allow for anyone to supply power to anyone other than themselves. But that may be changing slowly. We're hopeful that there will be changes in that, but you can power for yourself. You can't really sell power to your neighbor. No, that would not be legal. But moving into an aspect of what does a community style grid look like would require policy and regulatory changes to enable that beneficial energy management structure. So in the meantime, we can do what we can do for our own buildings as own entities. But again, coming down to policy and engagement, we need a lot more on in the incentive programs. We need to see development regulatory frameworks, collaboration with utilities, grid operators. We need some mandates for smart electrical demand management implementation. Public awareness campaigns are really important to continue R&D funding and training and certification programs. So quite holistically looking at it this way, lots of regulatory and support incentives that we need that can possibly be brought in that have been done in different jurisdictions, from feed-in tariffs, tax credits, grid modernization funding programs. Again, I mentioned the TOU, which is the time of use. So just, it's great to see also in Manitoba, we just have an integrated resource plan come out end of last year, finally. And so things are moving, but there's still a lot of things that need to happen, and there's different mechanisms out there to do that. So I just want to show you now a little bit of an interactive demo on what we have going on at CORE. The CoreEmpower House is one of our main products, and it is a home house that is its own microgrid. And it effectively, this is one example here, that is its own microgrid. It's connected, and it can island from the grid if need be, or be grid connected so it can sell power back to the grid. And I just want to show you a little bit of how it works on the energy flow part. So you can see when we're producing power, when we're discharging, when we're consuming, as well as when we're importing power. And then, of course, the other scenario when we are also exporting power to the grid, in this existing example. And lastly, I want to show you what happens with our Coreo Home product, this is a dashboard of our SEDM, which is our smart electrical demand management system, where we are able to see across time. This is just one example, what is happening. We've got our daily energy consumption. We know what is turned on with our different devices when they come on, and the different energy usage throughout the day, and what that looks like in terms of the used energy, and what is specifically using that energy. I'm going to hop to this next one as part of our demo. This is going to show you a little bit of how it works. You can see from the last 2 days, last 24 hours, what's happened in the last few hours, and just getting a rating of what is going on in the home, so that we have that smart energy demand knowledge going back and forth. And lastly, I just want to show you here what this looks like, going from like everything off to turning something on within just 6 minutes. This is a quick, I think it's like 6 minutes and 30 seconds, right? So you can see where we've had nothing on. We've turned on the car plug. We've turned on, excuse me, the living room lamp. We've turned on a TV and a different lighting. And we know when they're coming on and what that looks like, and how that is being tracked and monitored, when it's off, when it's on, and then how that is impacting the daily energy consumption. So that's a wrap on the first part, and we're going to go into the Q&A. I just wanted to say thank you so much. If you need to contact me, feel free to reach out anytime. My email is there, our website's there, and I'm on LinkedIn as well. So I'm more than welcome. Would love to hear from you if you have any questions. And now I'm just going to open up the floor to the Q&A. And Laura, if you want to help me with maybe some of the questions that might have come in, that would be greatly appreciated.
Absolutely, here to help for sure. So our first question is coming in from Kurt, and he's asking, are you setting up systems for customers as an independent contractor? How active is Manitoba Hydro in this space?
Yeah, so okay, on the demand side, I'm going to assume, Kurt, that's the question on the demand side, or on the supply side, or both?
Both, but yeah, both. I'm curious to know how active hydro is in the space that you work in.
Yeah. Okay. So on the supply side, yes, we are one of the Manitoba Hydro approved contractors. If you were to look for a supplier of energy systems, yeah, that would be us. But on the demand side, you don't see that yet. I feel like we're doing it, we're offering it for our customers. I don't see a call from that from Manitoba Hydro yet. That doesn't mean, like, I don't know what's internally they're processing or doing, but that has not come through on their side. I think they're still figuring that out and what that might look like. We would be more than happy to have a program like that. Of course, I think it's so important. But that's sort of what it looks like right now. Yes, on the supply side, in case you weren't aware, there is an incentive for solar panels in Manitoba right now. I believe you get 50 cents back per watt installed. So yeah, if you're interested in doing supply side stuff, there's a bit of an incentive in Manitoba. Plus the federal grant is $1 per watt, up to I think $5,000 for, so that'd be like a 5 kilowatt system. So essentially, you could get about, I think, 50%. Roughly, don't quote me exactly to have to do the exact calculation, but around 50% back on your installation costs for a basic solar energy system. But the demand side, we don't see that kind of incentive yet, and hopefully it'll be there. But yes, we do install this for customers and clients on the demand side as well.
Okay, thank you so much. I'm just going to go and order the questions, so hopefully they stack okay. So next is coming in from Bill saying, great info. Where would you integrate green infrastructure into your matrices so that the deciding tree shading, the residents, and the heat island effect are accounted for in energy conservation?
Okay, so I'm trying to find the question just to make sure I got all of that on there, but
he just sent it to just me, so
okay.
it's just looking for how like tree shading and other impacts of heat island effects are put into your accounting.
Yeah. So we're looking at it from the electricity side. Are you talking about like the heating side? We're not necessarily doing the insulation part or the impact of shading on heating, other than the impact of shading on electrical side. So if you have shading and you have a solar panel, of course, we're always designing to optimize that. So we always run our own shade analysis and ensure you get that optimized, because we do see a lot of poor installations that don't run that level of due diligence, and then we don't have the best built environment, and then it's a bad example of a technological installation. So we do that for the supply side. I'm not sure if you meant that for demand or supply, so forgive me if I missed answering a part there, but that's how I understood it.
I think you're doing great.
Okay.
So next is coming in from Cindy. Does distributed energy generation increase or decrease grid security?
Great question. So, this is one of those things, is how secure is your network? If we're thinking about like cybersecurity attacks, you need to have an extremely secure network. As soon as we're starting to transmit information, especially critical infrastructure, there's a whole other level of protection that is needed. And it's actually a very real threat, the cybersecurity issue of imagine shutting down power plants around the world because of this. So yes, very, very important. It's a very real threat, but that doesn't mean like your home is going to be shut down. We haven't seen that kind of level of threat. So on that level, I don't think individual homes are as threatened or seem to be as threatened as, say, like a large power plant or something like that. So there's different levels of security needs, different levels of threats, and it's very real. It's serious. Yeah.
Good. Follow or additional question from Cindy is it expected that battery storage and EVs will contribute to stabilization of power supply?
It's a good question. We've seen that it has in a lot of places, because it is a deployable energy. Like, it's deployable, it's dispatchable is what I'm trying to say. EVs can be seen like this as well. But what happens is that we're balancing this need with sudden demand. Like, say everybody comes home and needs to charge their EVs all of a sudden. What does that look like? The very real thing that's happening on the back end is, what level state of charge are you leaving your battery at? So, for example, our microgrid home also has EV charging. And so our user has a certain state level of charge for that battery to ensure they have autonomy in case there's a blackout or something like this. But with demand and with pricing, what we're seeing in behavior of the customer is that they are changing what level they are comfortable with in their level of their battery state of charge. So now they're dropping it a little bit more so that they can be using those electrons into their EVs or whatever other needs they may have. But the question comes back to now, okay, there's customer behavior and needs and market fluctuations. How does that impact the life of that battery, which has been designed to be optimally charged at like a 50% state of charge, or sometimes, it depends on the product and the OEM. You have to know how each device is designed and what their needs are. But there's tons of questions out there. So it's continuously evolving. Will it lead to greater stability or instability? I would say it should lead to greater stability. But of course, there are so many things that are up in the air. We've got balls in the air in terms of people coming online and when they're coming online. So monitoring that is so critical in being able to predict and prevent behavior and also mitigate anything that those fluctuations and things that might be unpredictable.
Okay, great. So Jana just put a note in here from Efficiency Manitoba that please note the incentives are through Efficiency Manitoba and not Manitoba Hydro.
Thank you, Jana.
And that CORE is a part of Efficiency Manitoba's registered contract network. So everybody can note that.
Thanks, Jana.
So the next question, the next question is coming in, asking, in addition to regulatory changes to Manitoba Hydro's mandate, what changes to expand the mandate of Efficiency Manitoba are needed to expand the use of SEDM in our province?
Oh, well, maybe Jana can answer that since she's here. But I don't want to speak on behalf of Efficiency Manitoba necessarily, but I can just, say that we definitely need to see something, right? And we definitely would love to see something set up for SEDM. I'm not sure if they're working on something or if I've missed something, but I would just defer to Efficiency Manitoba to find out what they are, what they're up to.
Well, even outside of what they're choosing to do, is there something that you feel like is needed to see happen? So there's what they're doing, but then also from your experience, is there something that you would like to see?
Regulatory changes?
Yeah.
Okay, yeah, there's many things I would like to see changed, but I think what's really important is we need more people. We need sort of a behavioral change, right? People have to be interested in the impact of this, but also to know that there's solutions out there. So how are we promoting this technology? How are we incentivizing people to make this change? What can, if Efficiency Manitoba is leading this, to see that leadership in the integration of the systems providers. So if it's our company or if it's others, to be able to offer in our local community and support local would be fantastic. But also regulatory wise, we need to have some changes in targets set that, one, preferably are not sunsetted. I think that's one of the challenges, and we've seen this fail many, many times in policies. If we have a goal and it's fantastic, there's sort of a lag in getting up to speed in informing industry and everybody who's supposed to support that, all our stakeholders. And then there's a sudden drop, which is called a sunset of that incentive. And that just can collapse an entire industry that has spent its time building itself up to support this. We're seeing this right now with the Canada Greener Homes Grant. It was supposed to be, I believe, a 7-year program, and now it's down to 3 years. Why did that happen? Why? That, it's just, there's so many questions around from industry we don't know. And then there's this level of all this effort that industry has put in and investing into supporting these incentives to make these energy transition changes and then have it just closed. And so I think that that needs to be stabilized. I think, seeing policies that are in place that are not based on government changes in government are absolutely critical to stabilizing investment and change in this era, and in something that is so new and people have so many questions about. There has to be stability, and if we want to have this transition happen, we need to know that there will be stability, because stability drives investment and de-risks all of this, whether it be on the supply side or on the demand side. So these transitions, they need to happen, and it's very critical that the policy is right and that we are thinking beyond government's time in office. We're thinking about programs that are there for a long time to stabilize this, because it's not going away. This is not something, the energy transition is not tied to government. This is just effect of our reality in life moving forward. So we need to get it right.